In this video, a neural network is used to estimate the loading of lines and transformers in the south grid. The aim is to analyze the effect of an increase in load in that area, with a quasi-dynamic simulation, but rather than using the standard load flow calculation, we will use the faster neural network approach. This artificial intelligence approach consists of training a neural network to approximate load flow calculations for a given electrical network topology, after which the neural network can provide a fast and good assessment of the network state for different operational conditions. To use the neural network functionality, the PyTorch library first needs to be downloaded, and the path configured within PowerFactory. This process is described in the Advanced Installation and Configuration Manual. The neural network commands are located in the Additional Tools toolbox. There is one command for the setup of the neural network, and one for the dataset generation and neural network training, which makes use of PowerFactory's probabilistic analysis function. Let us first look at the setup for neural networks command. Here, there is a link to the related neural network training command. We will look at this later. The neural network will be used with a quasi-dynamic simulation, so the load flow settings and result variables are taken from this quasi-dynamic simulation command. The network is trained using a training dataset, for which distributions are required. These can either be defined by the user, or generated automatically by the setup command, based on selected time characteristics. When the command is executed, the parameter distributions are created, together with estimated correlations. If required, the output variables of interest can be modified. In this example, the neural network should also be trained to approximate the line loading for an increase in demand in the south grid. To model this, a uniform distribution has been applied to all loads in grid south, and a distribution correlation is used to model the time-dependent correlation of the loads and generators. The command has already been executed in this project, so we will use the existing distributions and correlations. Now let us open the neural network training command. This can be used to generate a training dataset, and to use the dataset to train a neural network. Here, the method new is selected. With the continue method, an existing dataset is extended or the training of a neural network is continued. On the data generation page, there is a link to the probabilistic analysis command that has been used. Distribution correlations are considered, in order to model the time-dependent behavior of the loads and generators. The input variables are automatically selected, based on the defined distributions. For the output variables, the line and transformer loadings have been selected, using a filter to limit the results to those of the south grid. Limiting the output like this reduces the size of the neural network and improves performance. Alternatively, this option can be selected. Then, PowerFactory will automatically select the required variables as outputs, in order to be able, later on, to calculate currents, voltages and powers of all elements. On the neural network training page, the number of training epochs is specified. The command could now be executed. However, as the data generation and training process is computationally intensive and takes some time, this application example comes complete with a pre-trained neural network. The location of the neural network is defined in the study case. This plot shows the decreasing training error over epochs. If the outcome is not satisfactory, the continue function in the neural network training command can be used to expand the dataset, or train additional epochs. This button can be used to verify that the current network topology is the same as that on which the neural network was trained. Now, the neural network can be used in a quasi-dynamic simulation to analyze different load flow situations. For this purpose, an operation scenario has been created to model an increase in load in some parts of the grid and a decrease in other parts. Let us first return to the neural network object and use the Check Consistency button to check that the network topology in this scenario is the same as the topology in the scenario used to train the neural network. The quasi-dynamic simulation toolbox is selected, and the command is found here. The analysis will be carried out for a complete year, using a 1-hour time step. On the neural network page, the neural network is already selected. The command is executed. The reduction in calculation time is especially beneficial when a large number of time steps needs to be considered. The calculation is complete, and these plots can be used to examine the results for 2 lines of interest. We can see that for this line, the loading for this period of time is quite high. To validate the quality of this neural network approach, we will run a quasi-dynamic simulation with a standard load flow, just for this period. The results will be stored in a separate results file. The comparison in the plots shows us that the neural network calculation is in fact a good approximation to the results obtained using the standard load flow method.